All right, thanks for the introduction. I'm an undergrad at UC Berkeley. My name is Ankur, and I'll be presenting about cloud clustering, which is a data-intensive application on the cloud that uses purely the cloud services. So please feel free to ask me questions sort of in line with the talk. This is joint work with Microsoft Research. So the Wei Lu, Jared Jackson, who we're fortunate to have in the audience, and Roger Barga. So let's just get started. So MapReduce, Dryad, Twister, Hadoop, Spark, all of these are useful abstractions, frameworks for programming the cloud. MapReduce and Dryad supported asynchronous data flows, and their successors have added iterative computation to that. So what all of these frameworks have in common is that all of them, for communication and storage, they all implement their own systems using sockets and replication for fault tolerance. But cloud services like EC2 and Azure do natively provide some form of reliable communication and reliable storage. So the topic that I'll be exploring here is the question of whether we can build an efficient distributed application using only these cloud primitives provided by EC2 and Azure. The design goals that we have in mind here are, first of all, that any system should be efficient, but in particular for iterative algorithms, efficiency is paramount. And here efficiency comes in the form of supporting data locality and therefore supporting caching. Next, of course, fault tolerance. Fault tolerance is important, and we will introduce a few patterns to facilitate it. And then finally, the overarching goal is that any such system should support, should be cloud native, so should use the existing cloud services as reliable building blocks to create an efficient and fault-tolerant application. So here's the agenda for the rest of the talk. First of all, cloud clustering, which is the system that we built, is on Windows Azure, so I'll quickly go over it. It's Microsoft's cloud service offering. And then it implements the k-means clustering algorithm, which, I'll also give a quick overview of k-means. Next, next I'll talk about the architecture of cloud clustering, including the important design patterns that we used to build it and to make it efficient and fault tolerant. I'll go through evaluation of the performance and survey the related work. Okay, so first of all, Windows Azure is Microsoft's Windows and .NET-based cloud offering. It allows users to run code on VM instances that run on a pool of hardware in Microsoft's data centers. It also has a few interesting features, like when instances fail, it's able to recover those automatically. It also supports central blob storage, which allows programmers to upload large pieces of data to a central sort of EPS-like or S3-like storage service that's replicated and fault tolerant. But as usual with any network-based storage system, that's I/O bound on the network. So of course, reading from blob storage won't always be as fast as reading from local storage. And finally, it supports queue storage, which is a method of doing inter-instance communication using small messages that are reliably delivered. And these two latter pieces, blob storage and queue storage, are what will make up the fundamental building blocks of cloud clustering. Next, k-means is the algorithm that we implement as sort of a benchmark algorithm. It's a widely used, well-understood clustering algorithm that has plenty of applications. So it's an iterative clustering algorithm that groups n points into k clusters where both n and k are given, and generally n is much larger than k. It starts using an initial set of cluster centers, which are called centroids here. The cluster centers are randomly generated in this case, although there are modifications to improve the convergence speed. So then the algorithm steps through this flowchart where first it assigns all points to their closest centroids, and moves centroids to the average of their points, and repeats until convergence. K-means is pretty easy to parallelize, and that there's been plenty of work on this. So let's go give a quick summary of that. First of all, a master instance, or master VM, generates the initial centroids and loads the input data set into blob storage. Next, it partitions the input data set of points by splitting it across a bunch of workers, so the computation can run in parallel. On the workers, we execute the same steps as before for each partition. So each worker assigns the points in its partition to the closest centroids and computes partial sums that it'll send back to the server, which will allow the server, once it's received all the reports from its workers, to recalculate centroids and then iterate until convergence. Next, I'll go into the important part, which is how this is implemented using purely the cloud service, cloud building blocks. That is, key storage and blob storage. And here's where this is different from any K-means implementation on MapReduce or on other frameworks. The overall architecture is one of master and a pool of workers. So the master is a red block, and the pool of workers is here. And these two pieces coordinate using queues, which I described earlier, reliable message delivery system. So first, the master loads the input data set into central storage so that it's accessible by all the workers. It also generates the initial centroids in preparation for the iterations. And then at the beginning of every iteration, to launch the iteration, the master sends a command to all the workers, which includes a pointer to the worker's partition and a list of centroids for the worker. The workers do their computation as usual. They generate partial sums, and they return the partial sums to the master. Once all the workers have returned from this iteration, the master recalculates the centroids and launches the next iteration. We make two modifications here for efficiency and fault tolerance, and here's where the cloud building blocks come into play. First of all, since K-means is an iterative algorithm that uses large amounts of data in the form of that input point data set, data locality becomes an important concern. So here, first of all, the conventional method of building a typical cloud application is sort of a single queue architecture, where a master communicates with a pool of interchangeable workers by using a single queue, onto which it loads a bunch of tasks, and from which all the masters collectively dequeue and process the data. The advantage here is that workers are interchangeable and are stateless, which means that if they fail, that's no problem because it just reduces the throughput. But the problem here is that this single queue architecture is not suitable for iterative computation. The reason for that is that there's no data locality. Workers can dequeue tasks referring to different partitions of the input data set across different iterations, which means that there's no way to cache anything because the thing that we're caching will constantly be changing. So our solution to this is to split this queue up into multiple queues, one per worker, which unlocks data locality. So essentially, the master is able to send to give each worker an individual task, and to give it the same partition of the input data set every time. But this approach complicates fault tolerance because which I'll show soon. So here's our approach to fault tolerance while balancing efficiency. It's called a buddy system. So first of all, why is failure a problem here, really? Well, when a worker fails, what that means is it can't report its results to the master. And because the master is sort of operating on a fork join type model, it'll stall waiting for all the results to come back. What that means is that we need some way essentially to detect and to recover from failure. The buddy system is our approach to this. And so here, the conventional approach, going back to the conventional approach for fault tolerance, is to use heartbeating over sockets. So Hadoop MapReduce, for example, does this. There's a task tracker and job tracker that receive heartbeats, so essentially the master node knows when any instance has failed. Our design goals were originally to use the cloud services exclusively. And of course, the reason for that again is that it could make things simpler and more reliable in a concise way. So our insight in trying to adapt this pattern of fault tolerance to the cloud services is that when a worker fails, it's typically working on a particular task. And even though the worker has failed, the queue itself, the queue storage is guaranteed to be reliable. What that means is that we have some record of what was going on when the worker failed, and we can recover based on that information. So our solution here is a peer-to-peer system where the master assigns workers into buddy groups. And here, these are instances again, and these are their task queues. Normally, just the blue arrow represents each worker pulling its own task queue and pulling in tasks and processing them. But with the buddy system, every worker in a group, in a buddy group, pulls the task queues of all the other workers as well. So it's sort of a complete graph there. And so what that means is that when a worker fails, then tasks will come into its queue for a little while, and so it sort of will pile up. But once they've been in the queue for more than a certain timeout, it'll be possible for the other buddies to realize, that this buddy here that's failed is not moving forward. So they'll be able to dequeue the tasks and complete them. So this sort of breaks out of the stall pattern. It's also important. It's interesting to note here that the size of the buddy group here it's three workers. It could be any arbitrary number. It's a trade-off between fault tolerance and network traffic. I mean that a larger group is more resilient to simultaneous instance failure because if it's less likely for say 10 instances to fail simultaneously than it is for 3 instances, barring of course the Amazon type data center failure. At the same time, a larger group introduces more pooling traffic because there's sort of a combinatorial explosion in terms of traffic. Pooling traffic really is an issue here because in most cloud services, they charge per transaction. So there is some monetary cost associated with increased traffic. One approach to mitigating this problem of simultaneous failure is to use an Azure feature called fault domains. So fault domains expose information about the probability of simultaneous instance failure. And what that means is that if 2 instances are in 2 different fault domains as reported to us by Azure, then they're likely not to be in the same, for example, physical rack in the data center, and therefore will probably not be affected by a single point of failure. Also, the Azure SLA does provide some improved guarantees for instances in different fault domains, so that's a benefit. So we can take advantage of this information by spreading workers in a single buddy group across fault domains. So here, there's workers from 3 different fault domains, which provides extra resilience compared to if there were only one. I'll just stop here. Are there any questions? Just for now? Right. Okay.
I have one. Yes. How do you tell if a task is stuck in one of those queues because the node failed or because the node is slow?
Oh, that's
how do you
a good point.
Slowness versus failure?
Yeah. So we for now it's only a threshold-based kind of thing. So we each have a timeout, and the timeout adapts based on how long tasks have taken in the past. But it's true that in the first iteration we don't have any history, so there is some future work to be done there.